The momentum equation for a control volume. Before proceeding, it will be advantageous to develop the momentum equation for the control volume. Newton's second law states that the sum of external forces acting on a body in a given direction is proportional to the rate of change of momentum in a given direction. Writing this equation for the x direction, we can have Newton said that d mvx in the x direction on dt proportional to the forces. For the system of units used in this book, the proportionality can be written directly as an equality. dmvx as the second law of Newton. This equation has been written for a body of fixed mass, or in thermodynamics parlance, for a control mass. We now proceed to write the momentum equation for a control volume, and we follow a procedure similar to that used in writing the continuity equation and the first and the second laws of thermodynamics for a control volume. Consider the control volume shown in this picture to be fixed relative to its coordinate frame. Each flow that enters or leaves the control volume possesses an amount of momentum per unit mass, so that it adds or subtracts a rate of momentum to or from the control volume. Writing the momentum equation in a rate form similar to the balance equation for mass, energy, and entropy, we can write the momentum equation rate of change on the forces acting on the mass inside the control volume or on the control surface, and the flow of mass carrying momentum can be contributed to change of momentum. Momentum is conserved so that it cannot be created or destroyed, as was previously stated. The other control volume development. The momentum equation in the x direction for this equation can be written as this relation in the x direction: d mvx fx m dot ibix m dot EVEX. Similarly, for the y and z direction, we can write the relations d m vy on dt on the y direction, m dot I VIX, m dot EVEX. Or we can write for z direction as follow: m vz dt fy m dot I viz. Let me write some of the z direction plus and minus m dot EVEZ. In the case of control volume with no mass flow rate in or out a control mass, this equation reduces to the equation mv fx, for example sigma f, with no velocity and internal external flow. In this chapter, we will concern primarily with a steady state process. In which there is a single flow with uniform properties into the control volume and a single flow with uniform properties out of the control volume. The steady state assumption means that the rate of momentum change for the control volume terms are equals to 0. The momentum change on the control volume and D Therefore, for the steady state process, the momentum equation for the control volume, assuming uniform properties at each state, reduces to the form external flow z direction the y direction steady state. Furthermore, the special case in which there is single flow into the control volume, what is single flow? In and out, the relations can be simplified as force acting on a control surface in the next section.